No, ma'am.
Can I start?
Yes, ma'am. Yes, ma'am.
Okay. So today we'll begin with, yesterday itself we concluded with a small introduction about registers. So registers is a group of flip-flop, or we can tell first what is registers. Flip-flops can be grouped together to work in two aspects. One, just as a storage, second one for counting. When you're using it as a storage, then it is just called information storage, then it's called as registers. And when you're using it for counting purpose, then it is called as counters. So in this session, for another 4-5 days of classes, we'll be learning with what is flip-flop has a register we are going to learn. So yesterday we learned that there are types of registers. The types of registers are, so we saw there can be or parallel. So in serial, I told
your voice is breaking.
two types. One is left, another one is right. Parallel, we cannot up and down. Parallel. So now in these times, how the registers are going to be arranged and what we are going to do. See, these type of registers, whether it's parallel registers or serial registers, we can design it with E, we can design it with S.
No, we cannot hear, ma'am. It's very low, ma'am, your voice. Sometimes it's coming loud, sometimes it's coming low, ma'am.
Okay, okay. Now?
Now it's okay, ma'am.
Okay. So you can have it with flip-flop, flip-flop.
It's going low, ma'am, again.
Okay, one second, hold on. Hold on, students, just wait for another 1 more minute. Students, now is it okay? Hello, students? Okay.
Yes, ma'am.
Okay. So you can have D flip-flop, SR flip-flop, or you can design it with T or JK. Any of these flip-flops, you can design your registers as you wish, in which situation, what kind of application you have, you can design it with that. But most of the time, we know that D flip-flop is used as a buffer input, because whatever we are giving, if we want to transfer it, we can transfer the data one after the other. Now let us see the different kinds of flip-flops designed as a registers. Designed as a registers. Okay. Now, first one, we are going to see serial types. So as mentioned yesterday itself, serial types are of two types. That is, one is serial write and serial write input. But output is serial output. It will be obviously right side, means outside will be left side. So I'm just going to draw some data. So here you will start the input. So the data will start traversing like this. From here, after all this flip-flops traveling the data, then only you will take the data out. In the similar way, if we are going to take serial left input and serial output. So in that case, the block diagram will be, the input will be from this side, it will traverse one after the other flip-flop, and the output will be taken from your left-hand side. This is about your serial in, serial out. There is another one more thing also you have to know, that is parallel. How parallel things will happen. So parallel things will be like, if you want to know how to do parallel in, it will be the block diagram, and parallelly you will give input in all the flip-flops. Similarly, when you say parallel output, parallelly you will give in output will be taken simultaneously from all the flip-flops. This is about parallel in, parallel out. The in parallel things, it will be done simultaneously. On one clock pulse only, everything will happen. That is called as parallel in, parallel out. So you could have shown here only, that is not a problem, how to do parallel in and parallel out. Next there's one more thing which you have to know as a knowledge kind. That is rotate right, rotate right, and rotate left. So rotate right and rotate left means what? When you say rotate right, the diagram, you know, right shift and left shift, rotate circular, right shift and left shift, everything you know. So when I say right shift, the data will move like this. Finally, the output is not being taken. It has been fed back again to the input side. So there will be a circle, or after that, if you want output, you can pull it from here. But the output is fed for this one. So first time when I'm sending data 101, so it keeps going. So the whatever is the output, finally when you get 1 here, this will again be fed here. The cycle keeps repeating. This is your rotate right. Your rotate left will be on the opposite side. So the data will be given like this. The data will be given from this end. The rotate will happen from this end. So this is called as rotate right, rotate left, shift registers. So shifting of data can take place in any series, that is either right or either left or parallel or rotating. Okay, we should be ready to design any kind of registers. So now we are going to design the first kind of registers, serial in, serial out. We are going to have today three types of registers we are going to design and see, and then we are going to now hereafter you have to observe properly, because we are going to do what is actually, this is all just the introduction part. Now is what you're going to learn the basic concept wise. So the first type of flip-flop, we saw yesterday itself, there are 4 types of flip-flop: serial in, serial out, serial in, parallel out, parallel in, parallel out, serial in, parallel out. So we saw all this type of 4 types of flip-flops. So today we are going to see the first one, serial in, serial out. That means what? I'll just draw the block diagram, small block diagram. That means I'm going to draw most of the things I'll be drawing it for the 4-bit data only. In the exam, if they're going to ask the 8-bit data, the working is the same. Only thing is you're going to extend with 4 more bits. That's all. Okay. So this is serial in, serial out. So you can draw serial in right shift register, parallel serial out, or you can draw serial in left shift register. So right now what I'm going to teach you is left. That means from your right hand side, you're moving to the left. Okay. Anyways, you can do here. It is not important that this way only you have to do or that way only you have to do. So anything we can have even parallel right also. We'll see if right only first. So for then assignment will be for you left. So I'm going to draw shift register with parallel in. This is how parallel in, from one side the data you will get and the other side you will. Now things that you have to observe very carefully, listen. So I am going to draw. Okay, let me not tell you that first. Okay, now I have 4 blocks, or let me take 2. So I'm going to give a data 1, 0, 1. So when I give the first clock pulse, everything is reset to 0. So when I give the first clock pulse, the output produced will be, because there's no data anywhere, the output will be 0, 0, 0 on my 0 clock pulse. When I give my first clock pulse, what happens? This first one only will enter inside. This 0 would have shifted here. This 0 would have shifted here. So what happens when I'm giving the first clock pulse? This 1, because the serial in, at a time only one data can enter inside. So this first one will come inside. And the 0 which was there on the output side here, that will be fed as an input to the second register, second flip-flop. So what happens when I'm giving the clock pulse, whatever data is there in the input, that will be produced as an output. So now 0 is fed from the input to the output. So 0 will be the output. So for the first flip-flop, when I'm going to give the input, I'm going to give the clock, the input what is there 1, that only will be produced as an output. So 1. But for the second flip-flop, 0 was an input. So that only will be produced as an output for this one. So third one, 0 only is there. So 0 only would have produced as an output. So when I'm giving the second clock pulse, there will be shift like this. So the data is 0. So the first clock pulse will get data 0. This 1 would have shifted 1. This 0 would have shifted to the next flip-flop 0. So I'm giving third one. This 1 will now enter inside. So 1. This 0 will shift this side for the next flip-flop. This 1 will come here. This 0 would have already come out. So the fourth flip-flop, only you will get this 0, there's no data. This 1 will shift here. This 0 will shift here. This 1 we would have got as an output. So again on the fifth clock pulse, you would have shifted 0 would have been, this 0 would have been shifted here. This 1 would have shifted here. We would have got 0 as an output. Now you see on the fifth clock pulse only, that is number of datas, 3 plus n minus 1. On the fifth clock pulse only, you would have got the full data output. On the fifth clock pulse only, that is n plus n minus 1. So that is 3 bits plus n minus 1. So 2. So on the fifth clock pulse only. On the fifth clock pulse only, you will get the data output. Now we will draw it correctly with the flip-flop, and now see, I'm going to draw, basically now let me draw it for 4 flip-flops and show you how it is working. And we know that we are going to design it for the storage, so I will draw it with D flip-flop. So I have a D flip-flop, I have a Q output, I have, let me take it as A. So I have an input, I have a clock, I have an output. Okay, this will be my first A register. So let me say I'm having 4 registers. So I will design first 4 register connections. I will tell you. So I have the input, I have the output. You can design it for 3 also. It is your wish. D, Q, C, B. This will be B flip-flop. Just naming the flip-flop, that's all. And I will draw one more, because it looks nice if you put it as in the binary format. 3 all is not in the binary format. See, this D should not be confused with the D flip-flop. It is a 4th flip-flop named as D. Okay, so this all is a clock. So let us have a common clock pulse being given to everybody. And remember that I am going to work this circuit in a negative pulse. That means when it is 0, then only the circuit will run. So that the NOT will become 1 and then the circuit will be triggered for us. Okay, now you see we are working with serial in, serial out. Okay, now I have designed neatly that there are 4 flip-flops and none of the flip-flops are right now connected to each other. They are just connected with the clock and they are waiting for our connection. We are doing serial in, serial out. That means only the first one will be left free like this. Now, the second one output, the first one's output is connected to the second one. Okay, it's been connected to the second one. The second one's output is connected to the first one's input. Serially, we are going to connect the third one to the. Now we are connected the data serially. And we are resetting the flip-flops to 0, 0, 0, 0. Okay. 0, 0, 0, 0. Now, I am going to give an input. Let me say, I'm going to give an input 1, 0, 1, 1. This is my input. You know, in serial, they cannot be. Data has been given simultaneously, so they will be. So let us design a truth table for it. We will write 1, 2, 3, 4. So I'm going to write, please observe carefully. I'm going to write QA, QA, QB, QC, QD, and I'm going to write one more thing, very important, clock. And remember, my clock is negative pulse. So for the first time, I'm going to write on my 0 clock pulse, I'm going to have 0, 0, 0, 0 because I have reset all the flip-flops. I have nothing to do. Now I'm going to give the first clock pulse. When I'm giving the first clock pulse, what happens? This one which is here will get shifted here because I'm giving as an input. So when I'm giving an input and I'm giving a clock pulse, what happens? The output which is there at D, the same output will be produced at the Q. So what happens? I am giving the first clock pulse. I am giving the data 1. The data 1, A flip-flop will get the output 1. What will the B flip-flop get the output at QB? At QB, what they will get?
0.
When I'm giving the clock pulse, very good. When I'm giving the clock pulse, whatever was here, simultaneously the job will happen. When I'm giving here 1, this output is fed as an input here. So what happened? This 0 becomes an input here. This 0 becomes an input here. This 0 becomes an input here. This would have got vanished. Now, since their zeros have been shifted to their respective D flip-flops, so what happens when I'm giving a clock, the data which is there currently at each and every entry point, that will be an output. So now what happens, since here 1 is there, I've got 1. Here 0 is there, so I will get 0. B's output is fed to D's input, C's input. So output will be 0. This output will be fed here. This will become 0 and there will not be any output because there's no more connections. This would have been removed and we would have got. Then on my second clock pulse, I will get another 1 because this is second one is entering inside. My first one would have shifted to the next one. The next one 0 will be moved here. The next one 0 would have been moved here. On my third clock pulse, I will get a 0 input because my 0 input is 0. So 0. My 1s would have shifted just like that. Another 0 I will get because still it's retaining. On my fourth clock pulse, I will get this last one inside. 1, 0, 1, 1. You cannot say, ma'am, we have got the input. Whatever we have got the input, we have got in all the flip-flops. This can be the case of parallel out because we can take parallelly output. So simultaneously we'll get this output 1, 0, 1, 1. So we have got the output, we can say. So serial in, parallel out can stop till here. Because when you take drop down the outputs, you would have got all these outputs. So we can tell this as serial in, parallel out. But we are talking serial output. So the last one which we have entered, this one we have entered here, which is at A, should reach D. Then only we can say all the outputs are reached. So now 4 over. Now 5. So for 5, what will happen? We are going to move it. So since there's no data, we'll make it as 0, 1, 0, 1. We have already got one output we have taken out. 6, 0, 0, 1, 0. 7, 0, 0, 0, 1. Now you see 4 datas plus 3. This is not a clock pulse. Clock pulse starts from here only. So 4 plus 3, n plus n minus 1. So 4 plus 3. You see the last datas, all the datas would have appeared. So we have got 1, we have got 0, we have got 1, we have got 1. So totally of 7 clock pulse you require to get our output, the given output for the 4 bits of the output stage. So this is the flow chart. Oh, sorry, this is the truth table. This is the diagram flow diagram which works on the negative clock pulse. You should observe it should work on the negative clock pulse on the falling edge of this one. For the same thing, you can put this table and you can even show with the truth table. Sorry, timing diagram. You can even show with the timing diagram. The same flow table can be shown with a timing diagram. So how you can show with the timing diagram? Draw the clock pulse. So you should draw the clock first. We know clock 1, 2, 3, 4, 5, 6. So we are with the positive edge. This will become the negative edges. So let us say we are drawn a data D. So D is, so we may not be drawing D's flow. Okay. So now data. Okay, we will draw data also. It's not required. So, but tell what is the data? 0, 1, 0, 0. So we are going to write for QA, QB, QB, C and D. Let me draw it in different colors for representing. Okay. Now, on the first clock pulse, that is on the negative edge, you are going to start drawing the output. So the first one will be 1 for us. Even if it is 0, on the first negative edge, it's going to become 1. Okay. And what will happen to all this data? It's still 1, 0 for us. We are not on the till the next negative edge. Till the next negative edge, we are starting it from here. We are starting from here. So, we will take an. So on the first edge, we are drawing, we have a 1. So we have raised till the next following edge. So after that, we just hold on what happens. But for B, it will start only from here. For C, it will start on the next clock pulse. For D, it will start on the next clock pulse. Then only you'll get the data. So what is the next data? 0. So you bring it to 0 till the next clock pulse. You bring this till here. You bring this down. You bring this down. So till the next clock pulse, this one is 0. So I have brought it to 0. Next clock pulse, it becomes 1. So bring it to 1 till your falling edge. Okay, next clock pulse, this also becomes 1. For next clock pulse, this will become 1. For the next clock pulse, this will become 1. Again, you have 1 only. So retain it 1 only. Move till this. So move on the next. This, it should be next clock pulse. Again, after that, the datas are empty. So you bring back to 0 on the following edge and you start proceeding to remain 0. You see that till the last one comes out, it will be this one. So this will be your, see, stepwise your data will keep moving for all the outputs of QA, QB, QC, QD. Are you people understanding?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
If same thing has to happen for, so totally 7 clock pulses you will require for the complete data to come and reach outside. Okay. So for this